This is Fundamental Problem 17 from Chapter 16. In this problem, we want to determine the angular velocity of the link BC and the velocity of the piston C at the instant shown. So we want to find angular velocity BC and velocity C. So we're going to have to find the location of the instantaneous center of zero velocity. From the picture here, you can find the direction of velocity B. So the angular velocity is this way. So the velocity of point B must be to the left. And if velocity B is to the left, then piston C must be moving downward at this point. And actually, if you didn't know the direction of velocity B, as long as you know it's either to the left or to the right, and for velocity C, as long as you know whether, well, it has to be somewhere on this line here, either pointed this way or the opposite direction, you can still find the location of the instantaneous center. So draw a vector perpendicular to this, or draw a line perpendicular to the direction of the velocity vectors for both VB and VC, and they intersect at the instantaneous center. So we found the location of the instantaneous center of zero velocity. Then going back to page 362, let's just use this equation for the magnitude of the velocity, which is equal to the magnitude of the angular velocity times r, which is the distance from the instantaneous center to each point. So we can do that for velocity B and for velocity C. For velocity B, it's the angular velocity of BC times the magnitude of the distance to point B from the instantaneous center. And for velocity C, angular velocity times the distance to C from the instantaneous center. But these equations are just using the magnitudes rather than using the cross product. From the picture that they gave me here, I can also find the velocity of point B because I know the angular velocity of the wheel and I know the radius. So velocity B, the magnitude of velocity B, is the 6 radians per second times the 0.2 meters. And this gives me 1.2 meters per second. So now that I know this, I can use this with my equation here to find the angular velocity. First, though, I have to find this distance here. So all that I need to do that is to be able to find an angle. Well, this angle here is 30 degrees, which means this angle here is also 30 degrees. Which means this angle here, since this line was perpendicular to this vector, is 60 degrees. Since this is a right angle, this angle here is 30 degrees. And the length from point B to point C, that was 0.8 meters. Let me redraw this. So this is 30 degrees, and this is 0.8 meters. So that's enough for me to find RC from IC and RB from IC. So this is the hypotenuse. So I can say RC from IC is, well, let me do it this way. This is the hypotenuse. So if I do this times the sine of 30 degrees, that gives me the 0.8 meters. So that's 0.8 meters over sine of 30 degrees gives me the distance to point C from the instantaneous center. And if I want the distance to point B from the instantaneous center, that is the adjacent side. So RBIC is equal to that hypotenuse, which is 0.8 meters over sine of 30 degrees times cosine of 30 degrees. So now I have the distances that I need, so I can finish the problem first by using this equation here. So I get 1.2 meters per second is equal to the angular velocity times this 0.8 meters over sine of 30 degrees times cosine of 30 degrees, and this should give me for the angular velocity 0.8658 radians per second. And then I can use that down here to find the velocity of point C. So this is 0.8658 radians per second times this distance, which is 0.8 meters divided by sine of 30 degrees, and that gives me for VC 1.39 meters per second. And we found the direction or velocity C already, and we showed it on our diagram. So if you want to give that in your answer, it's 30 degrees below the negative x-axis. But let's just leave it as the magnitude there. So that concludes fundamental problem 17.